Here's the last part of our ellipse notes, where we'll be looking at how to draw the graph and how to take an equation that's not in standard form and put it into standard form using completing the square. So again, I have the standard forms here just to continuously allow us to reference back to them and to help you memorize these forms. But the steps for graphing are pretty simple. You want to plot the center of the ellipse first, the h and the k value. And then from that center, it doesn't even matter what a and b are. All that matters is that the number underneath x will be how far the ellipse stretches to the left or to the right from your center, because x determines your left and right motion. So whether it's a or whether it's b, it doesn't matter. The number under x will be how far you go left to right. Draw two more dots. And then the number underneath the y variable will be how far you stretch the ellipse up and down from the center. So start from the center and then figure out the horizontal and vertical stretching. Just connect those dots around the outside. So here's our first example, and since you can see that there's no number being added or subtracted from the x and the y, that means that our center is at the origin 0, 0. And then even though I know a is 5 and b is 4, that stuff doesn't really matter to me. I just care that the number underneath x, square root of this, is 4. So from the center, I'm going to go right 4 and left 4, because x dictates left and right motion for a graph. And then for the y value, the number underneath there is a 5. So in the y directions, up and down, I'm going to go 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So if you just kind of roughly sketch your ellipse passing through those points, you'll have a pretty good idea of the shape of the graph. Now I didn't plot the foci. We could find them, of course, because you do the a squared minus b squared value. So in this case, 25 minus 16 is 9. Square root of that is 3. So it would go in the same direction as the bigger one. So that would be up 3 and down 3. So I could plot a point here and a plot here for the foci, but those aren't actually dots on the ellipse. So if they don't ask you for them, you probably don't need to draw them. This example will only add the complication that now my center isn't at the origin. So I'm going to start off with the point 2, 1. Don't forget to change the signs on the x and the y values. So my center is 2, 1. Draw that dot. The number underneath x, square root of this is 2. So I'm going to go right 2 and left 2. And the number underneath y was 9. Square root of that is 3. So I'm going to go up 3 and down 3. And that's all it takes. We can just sketch our ellipse passing through those points. So you can see this one is stretched a little bit more vertically than horizontally. And that's it. So I've described this process once before, where we will be setting up completing the square and then using completing the square to get things into the standard form. It's pretty much the same process as what we did for our parabola. First, you want to get all of the x and y terms on the left side of the equation, though. Last time we kind of put some on the left, some on the right. For this, we have all the x's and y's on one side, and then all of the constants on the right side. Then you look for any coefficients on the x squared and y squared terms. If you see one on either x squared or y squared, then you need to factor that out from all of the x's or all of the y's, whichever one had a coefficient. There should not be a number attached to the squared terms for you to use completing the square. Then you would go through the completing the square process, and I'll show you that again in just a second, which will allow you to get the x's and the y's into a nice factorable form. Once you've done that completing the square, you should have ended up adding a bunch of numbers to the right side of the equation as you were working it out. So your last step is to divide everything by whatever number you have on the right-hand side of the equation. The reason you do that is because the standard form for an ellipse should always be equal to 1. Once you've done that, you should be in standard form for an ellipse. You might have to do some reducing of fractions or canceling. If there's something like 4 over 8, just make sure you reduce that fraction. But that's basically it for the work. So here's my example. They will either ask you to prove it's an ellipse, or they will say something about putting it into standard form using completing the square. So my first step here is to get all of the x's grouped together. So 9x squared and a negative 18x. And then I also need to group together the y's. So I'm going to have a plus 4y squared and the plus 16y. I'm just rearranging those things. They're still on the left side of the equation. However, the negative 11, I want to move that to the opposite side. So this will have a sign change when I move it to the other side by adding 11. Now there's a problem here because I don't want to have a number in front of the x squared or the y squared. So for the x's, I'm just focusing on the x's for a second, I'm going to take the 9 out. I'm going to factor it out. So 9x squared divided by 9, and then negative 18x divided by 9. And I'm going to leave my blank space for completing the square in just a moment. And then for the y's, I don't want a number in front, coefficient on the y squared, so I'm going to take 4 out of everything on the y's. 4y squared divided by 4, and then 16y divided by 4. Again, I will leave another blank space because for an ellipse, we actually have to do completing the square twice. So I'm going to take half of the middle number, which is negative 1, and square it. But here's the trick. I didn't actually just add 1 to the left side of the equation. Because of the distributive property, what I actually added was 9 times 1. So you have to be careful about that. And then the same thing is going to happen here. When I add a number for completing the square, I have to remember that it's actually 4 times that number. So for balancing out the equation, be careful to multiply whatever was factored out front. So 9 times 1, balancing it on the other side of the equation, I need to add 9. And then for this one, I take half of the middle number, which is 2, and I square it, which is 4. But I'm actually doing 4 times 4 on the left side of the equation. So if I want to keep both sides equal, I have to balance that out and add 4 times 4 to this side as well. Now you can use the shortcut for factoring. It's always the variable and half of the middle number squared. And the same thing for the y's. The variable is y. I left off the squared there. The variable is y. And half of the middle number squared. And then if I add these numbers together, 9 plus 16 is 25, plus 11 is 36. So we're almost done. The last step is that I need to set this equation equal to 1. So the way I do that is by dividing every single term by that 36. And there will be a little bit of reducing that I can perform because of this, because 9 over 36, for example, that reduces. So if I reduce the fractions, 9 over 36 leaves a 4 on the bottom. And then 4 over 36 also reduces. So then 4 over 36 leaves a 9 in the bottom. And then this is equal to 1. You'll notice that the coefficients that we had kind of end up flipping and being the denominators for the other one. So that's it. We've now put the original equation we had into the standard form for an ellipse. That's how we proved that it is an ellipse, because we were able to put it into the ellipse form. We couldn't have done that if it was some other shape. And so that's it for our notes on ellipses entirely. Next, we'll be looking at some very similar rules for a different shape.